Hi, welcome to online tutorial videos from JCBRO Labs. For more information and to download the source code of this video, you can visit us at www.jcbrolabs.org. Uh, we also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on Matlab, machine learning, data science, Python, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org, or you can also mail us your queries at jcbrolabs@gmail.com. Okay. So in this video, we'll talk about how to remove noise from a noisy signal in Python with the help of filters. Okay, so when a given signal is any signal is given to us, so just by looking at the structure or the time domain specification of the signal, we cannot determine like which frequency component are there and what should be the frequency component of it. So there is a specific procedure of it. First we go through the spectral information of the signal, and then based on our requirement we design the filters, whether it could be a low pass filter or high pass filter or band pass filter, and then finally we apply or filter the signal. So we will learn how to do entire this operation in Python. Okay, so let's create a new file. First we'll create a signal and we'll add a noise into it, and then we will analyze the spectral information of it, and then we'll move forward. Okay, so let's first save it. Okay. Noise remove, we can say it. Okay, so we need to import several files like matplotlib dot pyplot as plt. We have to import numpy as np. We have to import okay, from math import py, and we need to extract the FFT tool, because in our previous videos we have talked about how to do the spectral analysis in Python and how to design or analyze filters in Python. Okay. So import scipy.fft pack as sf, and import scipy.signal as sig. Okay. So first we'll close all the windows which may remain open. So plt.close all. Okay. Okay. Now first we will define a signal. We will simulate a signal in order to demonstrate it. So generate a signal. So as we know, generating a digital signal, one of the important feature is the sampling frequency. So first we'll define the sampling frequency of our signal, which is 100 Hertz, and then we'll define the time duration for which, or the length of the time for which we want to generate our signal. So let's say 4 seconds, and then we will generate the samples. So for generating a samples, we have a np.line space 0, t at the interval of sampling interval, so 1 by fs. Okay, now we'll define the signal frequency. Let's say we have a signal frequency of 10 Hertz, right? Okay, now let's generate a signal. X equals to np.sine 2 pi f into n. Okay, yeah, fine. And then let's plt.figure, and let's create first figure, and then plt.plot n comma x, and then we can put the title plt.title, sinusoidal wave, and then plt.x label, we can have time axis and seconds, right? And then plt.y label as it should be amplitude. Okay, so let's not generate, let's first have a look of this signal. whether we are getting the fine or not. Okay, plt dot plot and comma x cannot be as an integer np dot line space. Okay, 0 comma t comma 1 by fs. Okay, np dot arrange is the function. Sorry. Okay, so this is our sinusoidal signal. Okay, now we'll generate a noise. Signal is generated. Let's generate a noise. So let's say y equals to, there is a command np dot sig dot random. Okay, so there is a function like np dot random dot normal. So it generate np dot random dot normal. So it needs three arguments. First is the mean. So let's say we are generating 0 mean, then the variance, let's say 0.2 variance, and the length of the signal. So length of the or number of samples which we want to generate. So we can have np dot size of x, because it has to be a similar length. Okay, now let's generate it. And we can visualize this random number generator, because this function generates a random number in a Gaussian distribution. So if we do like plt dot histogram of y, then I think, yeah, so it is nearly a uh, Gaussian distribution. Okay, so all this is the additive white Gaussian noise ultimately which we are generating here. So we can write it additive white Gaussian noise. Right, now we can add this signal to our add this noise to our signal. So it is simply by addition process. So now it is a noisy signal. Okay, now we can plot it. So we can have noisy sinusoidal wave. Okay, so let's have for lesser duration, then we'll be able to look it clearly. Yep, so this is a noise which we have added, because the variance is less, so it is a less amount of noise. If we increase the variance, let's say 0.8, we'll find a high amount of noise, or the signal is corrupted with high amount of noise. Okay, now we will understand the spectral information of this signal, because sometimes only this much of information is present to us when someone is asked to denoise the signal. Okay, now from here main task starts. Like first of all we will do the spectral analysis of signal. So that's what we will do here. So plt dot subplot 2 comma 1 comma 1. Okay, now let's take the spectral analysis. So in order to do a spectral analysis, the simple task is, first we have to take the Fourier transform of the signal. So let's have x underscore f equals to absolute value absolute value of sf dot fft of x. So if you are not familiar with this, you can have a look at our previous videos in which we have talked about it a lot. And then we can have size and p dot size of x, and then we need to define the frequency axis. So for that, frequency axis defined by this, and because this FFT are double sided, so we require only one side spectrum, right? So in order to do that, we are doing all these operations. So np dot line space 0 comma 1 comma L by 2, half of the length which we are talking about. And then we'll take the magnitude part of it. So xl underscore m just to will take the half the length only into absolute value of x underscore f of 0 to np dot size of fr, right? And then now we will plot it. So plt dot subplot 2 comma 1 comma 2, and then plt dot plot. This will be fr comma xl underscore amp. Okay, and then we will put the title uh, spectrum of noisy signal. Okay, and then we can put the x label and y label. So let's copy it and paste it. So x label is frequency in hertz, and y label is the magnitude of the spectrum. So now let's have a look on the plot. Okay, one thing we have to do, we have to put the plt dot tight layout as well. Okay, st is not defined, it is sf. Yeah. So this is the signal and this is the spectrum of this signal. So it clearly shows like there is a frequency of 10 hertz around it, right, and all other is noise. So we can also, instead of this a linear scale, we can also put the plot in dB. For that we just need to change this magnitude into dB, and that can be done by multiplying it with 20 log 10. So it can be done in Python as 20 times log 10 of xm. Oh. Okay, so this is in dB, it's a spectrum in dB, right? We can also try to have a better look if we increase the number of samples, right? And let's, instead of 3 times we can have a 4. Yes. So here we are getting the spikes and all other is the noise, and this is a 10 hertz noisy signal with a sampling frequency of 200 hertz. So generally we are given with this, and this we have to do. Now we know this signal is of 10 hertz from this spectral analysis. Now we'll we'll create a filter. So for that we need a band pass filter. Okay, so we will need to create a band pass filter. So in our previous video I talked a lot about how to create filters in Python. So if you want to go through it, you can go through our previous video as well. Okay, so first of all we need to define, in order to define the filter, is the order of the filter and then the cutoff frequency of the filter. Now cutoff frequency is np.array, because it's 10 hertz, so we want to be from 8 hertz to 12 hertz, so that it comprised of this one, 8 to 12. So it comprised the 10 hertz signal within it, and then we need to convert this cutoff frequency into the radian per second form, or we need to normalize it, fc divided by fs, right? And then we'll design a filter b comma a equals to, and that is sig dot butter. Remember, order, the cutoff frequency, and the filter type. So we need to define the filter type. It is a band pass filter. Yeah. Now prior to running it, or prior to plotting it, let's have a look of the filter, the frequency response of the filter, and it is not N, it is O, as it is the order. Yep. So now we can have the frequency response of the filter response. Okay, so in order to do a filter response, we just need to use one of the command which is there, that is sig.freqz. Okay, and b comma a comma, now we need to define the number of words we want to have into it. So let's say 1024 number of samples, and then let's convert this w into frequency of hertz, because it is in normalized domain in radian per second, so we need to convert it into hertz. W divided by 2 pi, and now we can plot it. So plt dot figure 2, and then plt dot subplot 2 comma 1 comma 2, and then again have plt dot plot uh, this w comma 20 log 10, and that is h. Okay, we can put a title, plt dot title, that is a filter frequency response. Okay, now let's have a look on it. We don't get, okay, np dot log 10, it has to be np dot log 10. So these are the part of the programming. Yeah, so we are getting exactly the band pass, and if we zoom it, we'll find we have a center frequency of 10 hertz. So we'll apply this filter on it, and okay, it should be 1. Now we will filter the signal, right? And in order to filter the signal, there is a command sig dot L filter, and in this case we need to define the numerator and denominator coefficients of the filter, and then the signal which we want to filter it out, that is x, and that's it. Okay, now let's plot plt dot subplot, it is 2 comma 1 comma 2, and then plt dot plot and comma x underscore filt. Okay, and then let's put the title plt dot title as filtered signal, right? And plt dot type layout, TIGHT layout. Yep. Okay, so let's the numerator and denominator as well. Okay, let's run it. So this is a filtered signal. Obviously this is a high cutoff frequencies are not that much efficient, so we are getting the frequency of the filter is quite clear, but it is very much observable from the amplitude that there is a change in the amplitude, or we are getting the fluctuations in the amplitude. So moreover, this is how we provide or how we filter our signal, right? So in order to change this, there are several ways, right? Either further, there is also one thing you should notice, that at the starting part of it there is no response, so this is known as the filter delay, and that depends upon the number of samples which we are using in the filtering operation. So if we try to increase the filter order, let's say 10, let's say, because this is a IR filter, Butterworth filter, so sometimes it become unstable or not exactly unstable. We need to increase the, let's say, sample length. If we increase to 14, yeah, it is becoming unstable for filter order 10. So it has to be taken care while designing these filters, like what should be the sufficient order length of the filter. Let's say we are taking a 2, so it is second order filter. So second order filter is not that much good and specify and separating out the all the frequency components. Let's say do one. We'll have large noise content in the filter, but that is very much effective in this case. We have less distortion in the amplitude, we have less distortion at the starting as well. So it depends on application to application, right? So in order to design the filter, this has to be observed, like what is the output. So it is not a one-way process, we need to try different orders of the filter, and only select the filter order which satisfied are all the conditions. Yeah, so let's say we reduce the amount of noise content. Yeah, it is very much less because right now a less amount of noise is there, so less distortion in the amplitude. Okay. If we increase the noise, let's say 1.5, that is too much of noise. Okay, with a variance of 1.5, it doesn't look like a sinusoidal signal anyway, so we'll get output so like this. Okay, so there's a trade-off and all these things, right? And let's say sampling frequency we are having a 3 hertz, so we need to define here as cutoff frequency we need to change, right? So now it should be 1 to 4, or we can say 1 to 5. Let's run it and check. Okay, so this is a noisy signal of 3 hertz and this is a clear or filtered signal of 3 hertz. Okay, so I hope you learned a lot from this video, and I hope you learned how to design filter or unknown sinusoidal signal and how to remove the noise from an unknown signal and how to get the desired one by using the filter analysis in Python. So finally, we also provide online training, help in technical assignment. We also do freelance project based on Matlab, machine learning, data science, Python, Raspberry, Arduino, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org. You can also mail us at jcbrolabs@gmail.com. Okay, so that's it for this video. Thank you.